at the water around here. It's orange. Ew. Parents tell their kids it's tomato soup. But the truth is a much more interesting story. The answer begins down here, underground. A new world was discovered in the 18th century because of this. Coal. Here, at Worsley, in the northwest, commerce, necessity, raw materials and invention came together to kickstart the Industrial Revolution. Through that grill are 46 miles of coal mines, and 7 miles that way is Manchester. By the middle of the 18th century, Manchester was a boom town. Take a look around you even today, and you soon discover why. Linen Court, Loom Street, Cotton Street. The cotton industry is booming. It's not mechanised yet, but it's attracting lots of workers, and they live in places like this. The trouble with living here is you can't just nip outside and gather some firewood or cut some turf. If you want to keep warm and cook, you need coal, and you need it delivered here. Thank you very much. Things were reaching a crisis. Demand for coal was heavily outstripping supply. What the mine owner needs is a cheap and easy way of getting his coal to town. So what are his options? None. It's this or nothing. Horse and cart. It's hard work, it's slow, and with respect to Colonel there, you can't move very much. There's got to be a better way. The solution to the problem was found in the last place you'd expect, down the mine itself. Look, albino fungus. This mine goes down to 300 metres, and once you start going to those depths, you get problems. Whoa. Hang on here a minute, John. The problem with mines is that once you cut into rock, you get this. Water. And you've got to get rid of it because it runs downhill. This mine has to have 30 million litres pumped out every day. And this mine isn't even working. So, your mine's full of water. It's got to go somewhere. What do? You build a sump. So all the water drains to the bottom of the mine. Here's one. Then what do you do with it? Well, you've got to pump it out. And that is a pump. Trust me. And this is the engine that powers the pump. And it's a very special engine. This is a replica of a Newcomen steam engine, which was built for Lord Dudley's mine to pump water out. Thomas Newcomen, a blacksmith, installed this engine in 1712. The Duke of Bridgewater may well have thought about installing an engine like this in his mines at Worsley. It was a marvel of the age, a marvel which I will now demonstrate. Pardon me for not wearing my wig or my frock coat. Right. Fire. You can tell this is an early engine because you've got the firebox down here, the water in the boiler above it, and then jammed on top, the cylinder. This engine was designed to pump water out of a coal mine, and it's a good job because it absolutely eats coal. It is 0.5% efficient. So efficiency is not its strong point. Below us, we have our fire, heating the water in the boiler and above that is the cylinder. So we're now waiting to get steam in the boiler and to warm up this cylinder because we want to pump. This beam is doing the work. At the other end of that beam are the pump rods. Those rods go all the way down into the shaft and they will act as the pump. They work on the downstroke. They work by pushing the water out. They don't pull it up. So gravity is helping us. The end of that beam, the weight of those rods, all acts to force water out of the mine. But we want to bring the other end of the beam back up. And here's how Newcomen did it. There's the cylinder. We've now got steam. So by depressing this, what I can only call a contraption with respect to this venerable engine, this is the steam lever. We depress that and steam's admitted to the bottom of the cylinder below the piston. By releasing the F valve there, via this piece of rope here, water's also admitted then, and then the steam condenses, causing a partial vacuum below the piston. Atmospheric pressure then acts on that, pulling it down. So that pulls the end of the beam down and the rods back up. Then gravity works with the rods and the end of the beam. So we're pumping. OK, let's see if it works. I'm now going to drive a 1712 steam engine. Steam lever. Steam into cylinder. Release F lever. Water sit into cylinder. Fantastic. Now, that was just a single action. When the machine works properly, this cog lever here, see these bolts here, these act on the various levers. So it has an automatic action. A little bit like this.
In most mines, the water was pumped out into a nearby river and just went on its merry way down to the sea.
But here comes the piece of brilliance, the piece of lateral thinking. Why not use the water? Why not treat it as a resource? In the same way as you treat the coal that you've so heavily won underground. Why not use it to create a canal so that you can transport your coal to your points of sale? This brilliant, obvious, logical step came from the mind not of an engineer or a man of business or some hard-nosed chap. It came from a member of the aristocracy, one of the leisure classes, the Duke of Bridgewater, don't you know? Like most young, well-educated gentlemen of the 18th century, the Duke of Bridgewater was sent abroad on a grand tour to finish him off, a sort of gap year. He saw lots of Greek and Roman remains and brought a lot of them back with him, except that he never unpacked them, because after what he'd seen on the continent, he wasn't interested in art anymore. He was interested in this. 100 years before the English got round to it, the French were building flights of locks like these on the Canal du Midi, and even they were slow off the mark.
As early as 1500, Leonardo da Vinci was designing locks like these, with mitre gates. Before Da Vinci came along, most locks had gates with a vertical lift. But there's a big disadvantage to this system. Drop the gate and you're fighting water pressure. It's difficult to get a good watertight fit. Da Vinci worked with the water. The mitre angle means the water pushes against the gate to keep it watertight. Not only that, each gate pivots in the middle, making them much easier to operate. An efficient and effective canal system. This is what Bridgewater marvelled at.
The Duke of Bridgewater returned from his grand tour and decided to build a canal. to get the coal from his mines to the newly expanding town of Manchester. And he employed a promising, up-and-coming new engineer called James Brindley. Now, in this representation of what then happened, I shall portray the Duke of Bridgewater, and Gilbert, his surveyor, will be played by Vic here.
This was a momentous decision. Nobody in Great Britain had ever before attempted to build a canal that was not connected to the river system. So, which way to go? Well, building locks takes time, so if we can, we want to avoid the hills. The whole procedure was done using a simple spirit level with a sight lens, or as we know it now, a theodolite.
The first peg, first level, is Worsley, my mind. Okay, here we go.
The figures on the surveying pole are upside down, but they're not if you're Gilbert looking through the lens of the level. Now, take a level.
Right.
And then move along our route a set measured distance.
Down. Back up. That's it. Mark that.
And this is what they did, for mile after mile after mile. They followed the contours. They went round the hills. OK, Vic.
Up a foot. Up to me.
1, 2, 3, 4, 5.
Up to me. That's it.
We're now on the other side of the hill that we started from. But we haven't gone over it. We've followed the contours all around. Thank you, Gilbert, also known as Vic. So we're well on our way to Manchester. But we haven't built any locks. Brindley, Gilbert and the Duke of Bridgewater had got 4 miles from Worsley to this point without using a lock. But here they encountered a natural obstacle, the River Irwell. This was already a navigation, working, open to trade, ran by the Irwell Navigation Company. Brindley and Gilbert and the Duke approached them with a view to combining their interests, but were cruelly rejected, so they hatched a cunning plan. The Duke of Bridgewater, on his trips abroad, had probably seen aqueducts used, particularly on the Canal du Midi, and this was his idea, to cross the Irwell, to completely ignore the Irwell Navigation Company. So he gave the problem to Brindley, who brilliantly solved it. But Brindley had never seen anything like that. In a sense, Brindley was reinventing the wheel. It hadn't been done since Roman times. It was the first aqueduct in this country, and it was here. Ish.
Just like the Romans, Brindley built his aqueduct of stone.
This is one of the original arches, moved here as a memorial to Brindley, not to Denise.
Brindley's aqueduct may be gone, but what's here today is still one of the wonders of the waterways.
When the River Irwell was incorporated into the Manchester Ship Canal in 1890, the Irwell aqueduct was far too low for ocean-going ships to pass underneath, so it was replaced by this, the Barton Swing Aqueduct, designed by another great engineer, Edward Leader Williams. The middle swinging section is 100 metres long. This is big lads engineering. Temporary bridge keeper, relieved of duty. Thank you. Carry on. Bridgewater and Gilbert decided not only to build a canal from Worsley to Manchester, they used the water in their mines to get to this, to the coalface. They built a network of canals underground, down here.
Currently, it's too dangerous to go in the underground canals, but these are pictures from the last survey. You can see there's not a lot of room, and the deeper you go, the worse it gets.
And these are the boats that brought the coal out of the mine. This is a Worsley mine boat. Looks the part, doesn't it? It's long and thin. It's designed to go through tunnels. It was either punted or it was pulled along for the roof of the tunnel, or by ropes, or possibly by boys laid across planks and actually legging it out. It took coal out, either shoveled directly in, or in wagons, or in baskets. In short, it was an incredibly adaptable boat. And if you get really close and smell, it still smells of coal.
It was an incredible system, 46 miles of underground canals. It even had lifts to take the boats from one level to another.
Looks familiar, doesn't it? Same knees, same double-ended. Only now it's bigger, and we've now got a system. This system uses these and that. Once you've started moving things by water, you may as well expand it. It's a 200-year-old containerised system, and we still use the same principle today. Funny, no engine. This is the next development of boat. Now, the reason I couldn't find an engine is because this boat never had one. She's designed to be hauled. Now, with a good horse and a cart and reasonable terrain, could probably pull a ton or so. And now, if you built a plateway and had about 5 carts, you get about 5 tons. But on water, where all I'm working against is water resistance, a horse could pull about 60 tons. Scorpio at the moment weighs probably about 25, 27 tons. And once I get her going, she's off. So with a few good blokes, Alge, Josh, Patrick, Keith, we could haul this boat all day. The Duke of Bridgewater has built himself a super efficient transport system to get his coal to Manchester. And he's timed it perfectly, because there's an invention about to burst on the market that will guarantee increased demand for coal. Lucky chap.
At the same time as Bridgewater was building his canal, a young man called James Watt was working out how to improve the Newcomen pumping engine.
How's that, Doug? Very good. This boiler is supplying steam to an engine that is still doing its original job. It is therefore the oldest working steam engine in the world. And this is the type of engine that set the Duke of Bridgewater's heart aflutter. It performs the same function as the Newcomen engine. There's a balance beam connected to a pump rod which literally pulls water. The other end, we have the piston rod connected to the piston, and it is there that we find Mr. Watt's ingenious new development. This cylinder's got a lid on it, and this is where Watt made his breakthrough. The Newcomen engine relied on condensing happening within the cylinder, so the cylinder got hot, then cooled down. But Watt had an idea. Instead of condensing the steam in the cylinder, so the cylinder is hot, cold, condense the steam outside the cylinder. In this, a condenser, which is always cold, which means that the cylinder is now always hot, which leads us to the next breakthrough. So this is the cylinder that is now constantly hot. It has a lid on it now, so we can no longer rely on atmospheric pressure to force the piston down. But we now have a bonus because we can use steam because it's closed off. So steam now acts on both sides of the piston, like that. So we have a much, much more efficient engine. The Newcomen engine had a 0.5% efficiency. This is 5 times that at 2.5%. Not much, but hey, it was 1812. This engine is controlled from here. And this is Harry, who is the driver. Because even though it's a stationary engine, it still has a driver. Harry, what are you doing?
I'm controlling the steam inlet to the cylinder to maintain the stroke.
How many men would it have taken originally to run this engine?
It took 2 men and a lad.
There's always a lad, isn't there? We've got one. Will! Will! And that is this engine's job. Water. It pumps water. 1 tonne per stroke. 1,260 litres. 12 strokes, 12 tonnes per minute. There's another one. There's another one.
This engine's job is to pump water into the summit level of a canal. Engines built on this model, doing all kinds of jobs, would truly shape the world over the next 100 years.
The Duke of Bridgewater was one of those men who had exactly the right idea at exactly the right time. Everything was coming together for something momentous to happen. For the first time, we had an efficient transport system to get coal from the mines to the factories, and a steam engine to power the machines, to make the goods, and then back on the canal, and then the goods transported to the ports, to centres of population. Boom time! So, why is the water in the Bridgewater Canal orange? Well, it's all to do with the mines. Because when you get coal, you get rocks rich in iron salts, and when they come into contact with the air, they oxidise. So this is iron soup. Coal, canals, steam. And as we're going to see over the coming series, it was a magic combination. This is a beautiful boat. And you can hear that engine just really sweet, lovely. And I haven't steered a boat like this for 15 odd years. And it's a bit like riding a bike. It doesn't really get much better than this.